Hello, everyone. This is the part 2 of the atomic structure and interatomic bonding. So in the part 1, we're talking about the two atomic model, the Bohr atomic model and the quantum mechanical atomic model, and also the difference between the atomic model. And we highlight about the quantum mechanical principle that can explain with the electron energy that's orbiting around the nucleus. And in part 2 of this topics that we are going to talk about the interaction between the two atoms, the attractive force, repulsive force, and also net energies that between the two atoms. Then also, what is the state of the equilibriums of the two atoms? And then there will be different type of bondings like ionic bonds, covalent bond, metallic bonds, and also some secondary bondings like a hydrogen bond, and also the van der Waals bonds. Then we talk about briefly the different type of material having the different type of bonding. So let's go. The bonding force, the energies. So if there is two atoms, there will be two different type of force that's going to be occur between the two atoms. The first one is going to be the attractive force, and the second will be the repulsive force. So this attractive force, it's coming from the different type of the bondings between the two atoms. It's going to be covalent bonds, it's going to be ionic bonds, it's going to be metallic bonds. Type of these different type of bondings, the attractive force will be different. So another one is repulsive force. So the repulsive force is coming from the interactions between the electron clouds of the two atoms. So when the two atoms are getting closer and closer, there will be overlap of the electron clouds, the two atoms. And in this case, there will be formation of the repulsive force between the two atoms because of the two electron clouds are negatively charged and they will be repulsed each other. So when you take a look at the right side, the graph, the vertical line, as you will see here, there will be attraction force to the top, and there will be repulsive force to the bottoms. And these lines, horizontal lines, representing the distance between the two atoms. If the two atoms are far away from each other, there will be no interactions between the two atoms, and they will be getting closer and closer, and the attractive force is getting higher and higher. After that, at one point, there will be repulsive force between the two atoms. In that case, the attraction force, the net force, which is the summation of the repulsive force and attraction force, will decrease because there will be influence of the repulsive force, and at some point there will be the cancellation of the attractive force and repulsive force. That is what we call zero net force. And that is the distance we call it the equilibrium distance, because there will be no there will be the cancellation of the attractive force and repulsive force each other. It is not like there is no attractive force or there is no repulsion force. It is like the balance of the attractive force and repulsive force between the two atoms. This is we call the equilibrium distance. So at this equilibrium distance, there will be the higher energy that the bondings will be together. The energy that makes the bonds between the two atoms, that's which we call it the bonding energy of the two atoms. So this bonding energy is the energy of the minimum points at the point of the equilibrium distance between the two atoms. If you want to break down the bonds between the two atoms, you need to have the energy that we can see here between the two atoms. So let's take a look more clearly the simulations. So hydrogen atoms. When the hydrogen atoms are getting close and close and close to each other, and then at one point of the equilibrium state, they will stop not to getting closer and also not to go away from each other. So this is the energy which we call the potential energy or the bonding energy that between the two atoms. So I hope you will be clear about the bonding force and also the energies between the two atoms. So let's talk about the primary bondings. So the primary bondings between the two atoms, there will be three main types of primary bonding. So the first one is ionic bonds, the second one is covalent bonds, and the final one is metallic bonds. Okay, these kind of bondings, it's played by the valence electrons. What do you mean by that? What do you mean by the valence electrons? So valence electrons are the electrons that orbiting around the nucleus at the outermost shell of the atoms. So the valence electrons are how the type of bonding will be different. Okay. So the bondings, the formation of the bondings between the two atoms, whatever the type of bonding it is coming from because of the atoms, they want to be a stable nature. They want to have a full electrons in this outermost shell as it was defined in the part 1's electronic configuration structure. Okay, so that's what we call the outer stability rule. So the electrons, they have a few electrons in the outermost shell. They want to give that some of the electrons, they have almost full of the electrons in the outermost shell. In that case, they want to take more from the other. This is how electrons have a tendency of giving up electrons and taking back the electrons from the other atoms. Okay. So the bondings between the two atoms are played by the valence electrons or the outermost shell of the atoms. Okay, so to make it clear about the electronic configurations, so for the first shell, there will be 1s2, 2 electrons, and then second shell, there will be 4 electrons for the carbons, 2s2 and 2p2. But the more outermost shell is the 2p2, but there will be exceptional, like a sp2 hybridization. So in that case, there will be 4 electrons will be play as a valence electron for the carbons. It form me the C4 molecules. Pretty much like that. So let's go one by one. So the first one is the ionic bonding. Okay, before we talking about ionic bondings, I need to recall this electronegativity value of the periodic table. For left to right side, the electronegativity value is increased. So the electronegativity value is how the elements have the energy that they want to take the electron from the other to have a full electron configuration structure for their atoms. So in this case, fluorines have the highest electronegativity value. These kind of elements, they want to take the electron from the other very happily. Okay, let's go to the ionic bond. So ionic bonds, it found by the transfer electrons between the two sharply different electronegative elements. So it's going to be like, one element is going to be left side of the periodic table, another element is going to be on the right side of the table, because that is how the two sharply different electronegative elements. That's why left side is the metallic elements and the right side of the periodic table is non-metallic elements. So the ionic bonding is formed between metallic elements and non-metallic elements. Okay, for example, sodiums, and the chlorines. The sodiums is a metallic element, and the chlorines is a non-metallic element. The sodium have a 1 valence electron in the outermost shell, and the chlorines have one empty electrons in the outermost shell. So in this case, sodium and chlorines, the sodium just only one electron, so they're willing to give the electrons, but chlorines is almost full, so they want to take the electron from the other, and then sodium and chlorine match as one point, and there will be transfer electron from the sodium to the chlorines, and then sodium became sodium ions, the chlorine became chlorine ion, and then in ion form they just like the positive charge and negative charge. This is the Coulomb interaction between the two atoms. Okay, so because the completely transfer the electron from one atom to another, and the bondings surroundings of the atom are equal to all directions. So that's why this kind of ionic bonding is non-directional, and also these bonding material which have the ionic bondings have half and brittle, and also the insulated internal the electrically and also thermally. So this is about the ionic bonding. So the second one is covalent bonds. The covalent bonds is formed by sharing. This is sharing electrons between two similar electronegative elements. So that means the elements that form the covalent bonds, they are sitting next to each other at the periodic table. For example, silicon. So silicon have a 4 valence electrons in the outermost shell, and then to complete the 8 electrons in the outermost shell, they will have 4 bondings with a neighbor 4 silicons atoms to have a complete outer energy shell of 8 electrons. Then you will see here the 4 electrons in the outermost shell, and then they will form the 4 bondings between with the 4 other atoms of the silicons, and then because the sharing of the electron, there is a covalent bond because the sharings one particular atom and atom of the silicon, so they will be like the directional. This sharing, it's not distributed the whole thing, but this sharing between this specific particular electron, it's just only one particular atoms. So this is one directions, not into the direction of the other ones. Okay, so that's why we call it the directional bonding. So this covalent bond is the directional bonding, and it's because of that this is very hard and also very high melting points. And also these covalent bonded material are electrically insulated, but depend on the type of the material, the elements found the bondings. It could be the semiconductor, like a dopings, maybe p-dopings or the endopings. Okay, and also this mechanical property of these covalent bonded material are very brittle. And the next ones is the metallic bonds. I like metallic bonds. I want to be like a metallic bonds because the electron in the outermost shell are freely sharing to each other, and they are not going into particular elements, particular atoms, and they are moving freely each other. So the metallic bonds between the metallic elements in which the element became the electropositive atoms, because all the atoms of these elements are willing to give the electrons. They want to give the electrons to all neighbor atoms, and then they themselves became like electropositive atoms. So that's why the core is like electropositive, and the electrons became a cloud of electrons. Electron clouds is the sea of the electrons surrounding around the atoms. For example, aluminiums have a 3 valence electron. These 3 valence electrons will be given to all the neighbor atoms, and they became themselves like a positive ions. So these electrons are going around all the atoms in the material, and this is all about the metallic bonds. So because of the freely moving electrons around of the atoms, they are very good conductor of electricity and also heat conductor because of the free electrons. And because of these non-directionals bonded of the metallic bonds material, these metal and their lines are defined manner, and also we can see there was the significant amount of the deformations before the fracture of these metallic bonded material. So now we briefly talk about the ionic bonds, covalent bond, and metallic bond, and these are the primary bonding. So let's go to the secondary bonding, or we call it the van der Waals bonds. So secondary bonds or van der Waals bonds, whatever it is, they are very weak compared with the primary bonds or chemical bonds that we already talked before. So these secondary bondings, it's coming from the atomic or molecular dipole, that's the existence between the positive and negative portion of the ethanol molecule. And because of the positive and negative atom of the molecules, there will be Coulombic attraction between the positive and negative atom molecule, maybe dipole, and also to the adjacent atom. For example, if there is the attraction between the two dipole atoms, and in that case, these two atoms could be dipole dipole molecules, or maybe one is dipole, another one is induced dipole, or maybe polar molecule, and maybe between the two polar molecules. And for example, the hydrogen bondings mostly is found between the hydrogens existing molecules at one constituents in this molecule. So in this the first figure it's like the atoms, one side positives, one side negatives, right? Is a dipole. And this dipole and dipole, and there will be the interaction between these two dipole, and we'll find the van der Waals bonding. And at the same case that we can put it into the similar concepts, hydrogen fluoride. Hydrogens and fluorides found the bondings, okay, and then there will be in the hydrogen side there will be the positive because of the electrons was shared with the fluorines, and the fluorine have a lot of electrons, the atom share, and this side is going to be negative, but the hydrogen they already share to one particular the electron to one particular atoms, fluorines, and that this side is going to be positive. So positive and negative sides, and this negative side and this positive side will be like hydrogen bonding. Actually, this is we call the secondary bondings, and generally. Okay, another ones, if we one atom is a dipole, positive and negative, and the another atom if the symmetrical ones. So the electron are symmetrically distributed around the atoms, but one is already dipole. In this case, one positive and one negative. So these one negatives were going to induce to these symmetric atoms in such a way that electrons, if on one side, at that time there will be the van der Waals bondings from one dipole and one symmetrically maybe atom or molecules. For example, hydrochloric acid. So when it's dipole, on that side is positive sides, on that side negative side, but one is symmetries, and then this induced to this symmetries at a molecule, and there will be the van der Waals bondings that between the two atoms. So these kind of bondings generally, that's I try to explain briefly. It's about the secondary bonding or maybe van der Waals bonds. And let's talk briefly about the mixed bondings and the classification of the material. So the first figure on the angle of this triangle that you will see here, at the angle, the ionic bondings, metallic bondings, covalent bondings, van der Waals bonding. And the connection between the covalent bonding and metallic bonding is a covalent and ionic mixed bonds. And covalent and metallic is going to be like a metallic and covalent mixed bonding. And this one, a metallic ionic bonding. So the ionic bonding is found in the ionic material. A metallic bond is found in the metallic, very simple. And covalent bond is mostly found in the polymer. And the van der Waals bond is mostly we can see in the molecular solids. There is the interactions of the van der Waals bonding in the molecules in the organic molecule mostly. And so there will be the kind of material that's between the polymer and the metallic, which is a semi-metal, we call it metallite. And also the ionics and the metallic is called the intermetallic material. And between the polymer and ionic, it the ceramides in these regions. And the upper closest to the covalent bonding is a semiconductor. And this one's van der Waals bonding, which is happening at the molecular solids. So this is just general information about mixed bondings and also the material having the one particular bond or maybe the mixed bondings in one particular material. So I hope that you will enjoy this part 2 of interatomic force and then the bondings between the two atoms. Thank you very much.